Hi, welcome to the Bioinformatics Chat. Today I'm speaking with Mikhail Kolmogorov. Mikhail is a PhD student at the University of California, San Diego, at Pavel Pevzner's lab. And we will be talking about genome assembly and the assembler that Mikhail works on, which is called Flye. Mikhail, welcome to the podcast.
Hello, Roman.
Mikhail, tell us a bit about yourself and your background.
So I'm originally from Ekaterinburg, and I moved to St. Petersburg for college. I did my bachelor's in applied math, and then I found about this exciting program in bioinformatics in St. Petersburg University of the Russian Academy of Sciences. It is a very small school near St. Petersburg Polytechnic University. There's maybe 100 PhD students, and I think now they have master students as well. And they had this small program in bioinformatics. So I enrolled, and initially I wanted to simply work on fun computer science problems and write algorithms, implement them. I wanted to become a good coder, programmer. And then I realized that I actually like research. I like bioinformatics, and I like writing papers. I like basically doing some new stuff. And I graduated from this master program in St. Petersburg, and then I went to UC San Diego to start a PhD program 5 years ago, I believe. And now I'm here. It's been 5 years. I'm almost done with my PhD degree, hopefully. And I'm excited to tell you more about stuff that I'm working on.
So you're working on the assembler called Flye. Is that the project that you started in the lab, or was it already going when you arrived?
That's a good question. So this is not the first project I've been working on. So I was working on Flye for maybe 2 years, maybe a little more. And like there were some other projects on different topics that I've been working since I started my program. Regarding Flye, there were some efforts going on in the lab. It was a previous some previous students and postdocs in Pavel's lab. Yuan, who used to be a postdoc, and he's now a professor in Australian National University, and another PhD student, Jeffrey Yuan, he recently graduated, and he's now at Illumina here in San Diego. It's a big biotech sequencing company. So they've been working on a precursor to Flye called Bruijn. And this is where they were developing the methods for finding overlaps between long and noisy reads. And the idea was based on this frequent solid k-mers. And it became the part of Flye. So I joined the project on this stage. So, since these guys were working on Bruijn, and there was another sort of independent project, independent efforts on consensus calling and polishing, because in long reads we typically separate the structural assembly, and then once you have the structure, you also need to get your nucleotide-based quality you need to get it right. And this is almost like a separate problem. And so these guys were working on this as well.
So that's what you call polishing?
This is polishing.
And there is an interesting story behind the name Flye. Do you want to tell it?
So the story goes that Flye was a French mathematician, I believe. And, well, Flye is his last name, I think. He's been working on the Bruijn graphs as well. And he was actually the first to prove some facts about the Bruijn graph sequences, what we now call the Bruijn graph sequences, but at this time it was just some like binary sequences. And he was the first one to prove, I think, the fact about the existence of the Bruijn sequence. So the Bruijn sequence is basically originally it used to be defined over the binary alphabet. So it's a binary sequence such that it encodes all possible substrings of length k. So now we denote this as k-mers. And you want to find a minimal sequence like this. And like at this time, people didn't know if the sequences even exist. And I believe this mathematician, Flye, and I'm pretty sure my French pronunciation is not correct. I apologize for this. But he was the first one to prove the existence of these sequences for binary alphabets. And De Bruijn was working on these sequences as well. And they got his name. But De Bruijn himself acknowledged that Flye his work was one of the first work on this kind of sequences and graphs. So this is why we picked this name.
Very cool. And I should probably explain the connection. So the De Bruijn graphs that are used for assembly, they were also used to prove the existence of this De Bruijn sequence. So,
that's correct, yes.
Yeah. De Bruijn sequence does not simply share the name with De Bruijn graphs. They're actually connected.
Oh,
and
of course.
Later, De Bruijn graphs were utilized for genome assembly. And so, as we know, De Bruijn graphs are one way to do genome assembly.
Right.
But there are all sorts of different graphs used for assembly. And today we will talk about your own flavor of these assembly graphs. But can you make a brief general overview of like the various graphs that are used for assembly?
Right. So I think historically one of the first and very sort of natural approaches that was proposed was overlap graphs. So I sort of need to do an introduction of genome assembly problem in general, right? But it's very simple. So you have the goal is to read the sequence of a genome, and it could be a small genome, and people historically started to work with small viruses and phage, and then they started to analyze more like complex genomes such as bacteria, and then they moved to eukaryotes, to Drosophila, and then finally to humans. And the technology does not allow you to sequence the entire chromosome sequence or genome sequence. Instead, you can only sample short substrings of this sequence called reads. But you can sample as many reads as you want generally. And so what your results into would be a huge set of these short overlapping sequences, reads. And then your computational problem is, given these short sequences, you need to assemble them back into the original chromosome, original string. And a very natural idea is that, okay, if you have two reads that overlap, right, that share a sufficient overlapping sequence, they probably come from a related region of the genome. And this way you can take all your reads and define them as nodes on your graph, and you will connect the overlapping reads with an edge. And this structure, this graph is what people call overlap graph. And basically it encodes your, there exists a path in this graph that encodes your genomic sequence, because you can traverse from one read to another read and so on, and this way you can traverse your original chromosome. And now the problem is how would you find this path corresponding to your original sequence? And these are like different sorts of algorithms for doing this, and it depends on the genome size, and the genome complexity. And there are like many different flavors, and it applies also to different sequencing technologies. So but the original idea is you put a node for each read, and you connect to nodes with an edge if these two reads share sufficient overlap. So this is overlap graph. And this approach was very popular for, so it's historically, I think, used to be the first approach that was proposed. I think in early 90s, maybe even before. And it was also popularized by Gene Myers, who used to be a researcher at Cellular Genomics. And this approach was first applied for Sanger sequencing reads that were roughly 1,000 base pairs in length. And for comparison, a simple bacterial genome is several million base pairs. So your reads are like basically 100,000 times shorter than your genome. And so they basically were working on whole genome assembler, and this was resulted into something called Cellular assembler. And they used this assembler to assemble Drosophila genome first, and then they actually used it to assemble human genome, at least parts of the human genome during the human genome sequencing project. And there was an alternative approach that was proposed a bit later, I think in the middle of 1990s, and it kind of so people began to implement it in early 2000s, I believe, and this is called De Bruijn graph. And this is like, this was based on these De Bruijn graphs that we were just talking about. And originally, I think proposed by Mike Waterman's group. And my current advisor, Pavel Pevzner, he used to be his postdoc, so he used to work on these De Bruijn graphs, and I believe he's one of the people who actually like popularized this approach, and this resulted into many practical assemblers later on. And this approach was originally proposed for Sanger read, the Bruijn graphs approach, but it turns out that it was actually much more useful for the next generation of sequencing technologies, such as Illumina sequencing. And this is how we denote this this set of technologies, next generation sequencing technologies, right? And the difference is with Illumina sequencing, you get much shorter reads. Instead of 1,000 base pairs, you can get 100 base pairs, and even shorter. It was even shorter at this time, maybe 50 base pairs. On the other hand, you can produce these reads in parallel very quickly. And this was by the orders of magnitude cheaper than Sanger read sequencing. And this is why most of the people switched from Sanger sequencing to short read sequencing really fast. And it turned out that De Bruijn graphs were actually very useful in case of short read sequencing, because with short reads you get shorter fragments, but the number of fragments is significantly higher. You get significantly more fragments than you would get with Sanger reads. And as a result, in overlap graph, you need to compute pairwise alignments between all read pairs. And it became very expensive for massive short parallel sequencing because the number of fragments is so much higher. And on the other hand, in De Bruijn graphs, you don't need to do pairwise comparisons between reads. Instead, you're using these k-mers to build the graph. And this was one of the reasons why De Bruijn graphs became so popular, I believe. And short read sequencing, I think it was most of the popular genome assemblers based on short read sequencing were based on the Bruijn graphs.
So the Bruijn graphs are more efficient than overlap graphs for assembly because you can quickly build them. But do we lose anything when transitioning to the Bruijn graphs? Are there any downsides?
So you use some connectivity information because to build the Bruijn graphs, you split your reads into shorter fragments called k-mers. And typically, if you have short reads of length maybe hundreds, then you will be working with k-mers of size maybe 50. And you will be basically building the graph from this like shorter substrings. And this is why you sort of lose some long-range information from reads. But this only happens during the stage when you build the graph. So once you build the Bruijn graph, you will then reuse the information from reads by, so what assemblers typically do, they build the graph and they map your original reads back on this graph. And then they try to simplify this graph, based on this path that's like based on this read path that reads induce on the graph. So yes, you're sort of losing the connectivity information during the graph construction, but then you still have access to reads information, and then you can trace how reads traverse the graph, and then you can simplify this graph. So in the end, you both overlap and the Bruijn graph algorithms should, in the end, they should theoretically produce the optimal assembly given this set of reads.
Okay, so we've covered the Sanger sequencing, we've covered next generation sequencing, but next came long read sequencing, and how did that impact the art and science of assemblers?
Well, it impacted, the impact was huge, and basically it turns out that people needed completely new algorithms to assemble long reads. And this is because of two things. So long reads are basically much, much longer than Illumina reads. So for comparison, with the current Illumina machines, you might get, I think the maximum would be 250 nucleotides reads of this length. And you might get pairs of these reads, right? So you might get pairs of reads of 250 and separated by maybe 500 nucleotides. And then with long reads, you can routinely get tens of thousands nucleotides long reads. And the current people are also interested in increasing this length. And currently with there exist some protocols called ultra long reads. And with these protocols and with PacBio and Oxford Nanopore sequencers, you might even get reads over hundreds, thousands, and I think some labs will manage to get even millions of nucleotides long reads, and this is super exciting. On the other hand, the problem with these technologies is that error rate is so much higher. So for Illumina reads used to be very, very accurate. So the error rate was less than 0.1%. So for a read of length 100, there's like a high chance that there are no errors in these reads at all. And the error modes were also very convenient, because Illumina errors were just space substitutions. For long reads, for PacBio and for Oxford Nanopores, the error rate is roughly 15%, 10 to 15%. So compared to 0.1%. And then the errors are mostly insertions and deletions, and they are much harder to handle in the algorithms. So bottom line, you get much longer reads, but the error rate is also much higher. So, and you need new algorithms to handle this data.
And there already exist some algorithms that can cope with the specifics of long reads, right? Mm-hmm. What are the issues with those assemblers that you try to correct in Flye?
Okay, so historically, initially people were trying to do this as follows. Basically, they said, okay, we had these very noisy reads. Let's try to error correct them first, and then reuse the existing assemblers because the existing assemblers, such as Celera assembler for Sanger reads, that is based on overlap graphs, was basically designed to similar purposes for like Sanger reads were longer than Illumina reads, 1,000 base pairs long. And this was somewhat similar to what early long read studies were getting. And the idea was, okay, let's error correct these reads somehow, and then simply feed it to existing assemblers. And that's what people did. And they initially were trying to error correct PacBio. So PacBio was historically the first long read sequencing technologies. And they used to error correct PacBio reads with Illumina. And this is because, of course, was like challenging by itself. So you need to map these short reads to your long and noisy reads. And then you basically substitute the parse of, the mapped parse of long reads with your, short Illumina sequencing. And then you continue to do this with like next, Illumina reads and so on. And in the end, you theoretically will get like a accurate and long reads, and then they were using Celera assembler to get your final contigs and chromosomes. And then like the next studies, they were trying to error correct PacBio reads without any extra information. So this is something that was called self error correction. And the idea is similar. So you somehow align, you do pairwise alignments of all PacBio reads, and you take one single read and you have all the other reads that aligns to this one. And then you try to sort of compute a consensus of multiple reads, which will result into like, sort of more, confident sequence. And then you can feed these error corrected sequences to the, Celera. And so this is something that, people are still, I think this is still a dominating approach. Error correct first and then assemble. And, the first assembler was, called PBCR, I believe. And, then there were two more popular assemblers that are still being used, and like they're still the most state of the art. First one is called Falcon, and it was developed in PacBio at that time. And the other one is called Canoe. And Canoe is interesting because it is sort of a fork of Celera assembler. So it borrowed a lot of code and a lot of ideas from the original Celera assemblers, and even the original software engineers who worked on Celera assemblers now working on Canoe. And I think this is very exciting. So if you think about this, Celera assembler was developed 20 years ago, and it's still being used and it's still being sort of, so I think this tells us something about the quality of the work that people did in the past. Anyway, so the problem here is that this error correction step is very, time consuming, because you still need to compute all versus all pairwise alignments, and the errors make this problem very difficult. So the higher error rate you need to tolerate, the more difficult your, alignment procedures will be, the more like it kind of like expands your search space. And I mean, many groups were working on improving the speed of error correction step. But, something that we wanted to initially implement in Flye and in its precursor Bruijn was, what if we do not do error correction? What if we just try to assemble the raw PacBio and Oxford Nanopore reads, and then and we can assemble, maybe we can assemble the structure of the genome, and then we can error correct. And this way we can skip this error correction step, and this will result into like a significant speed up. And so Bruijn was one of the first assemblers that sort of implemented this paradigm. There was another one called Mini-Asm, and I think they were released. Mini-Asm was released a little earlier, and Mini-Asm was actually it became a very popular assembler as well. It is created by Han Li, who is also he's one of the, I think, one of the most famous hackers in bioinformatics. So he's the one who created the popular alignment tool BWA. He has some other work like population size estimation, and a couple of years ago he started working on genome assembly, and he created this mapping tool called Minimap, and then used it to in assembly of long reads and this resulted into a tool called Mini-ISM. So those were the first two, I believe, assemblers, Mini-ISM and Bruijn, that did not require error correction, and they were faster than these what we call here hierarchical approaches, such as and assemblers such as Falcon and Canoe.
So give us some numbers, some timings to grasp the magnitude of what we're talking about here. So if you were to assemble, I don't know, what do you usually assemble? Do you assemble a human genome? Do you assemble some kind of E. coli or a virus?
We try to assemble different genomes. We try to make sure that Flye works well on wide range of genomes. So currently Flye is faster than the early hierarchical approaches, but also I must know that like other assemblers are getting faster as well. So they're like getting optimized, and even hierarchical approaches they became faster. So I think for early studies for this PBCR tool, they were assembling Drosophila, and Drosophila is one of the most important model organisms. And they basically reported that they needed a few CPU years to assemble it initially. And they obviously had a good, I think, very powerful computing cluster to perform this assembly. And this was basically because Drosophila genome has a lot of repeats, and the more repeats you have, the more difficult your alignment becomes. And of course, it is optimized now.
So out of those 2 CPU years, how much would you estimate would go towards read correction?
Well, most of it is read correction.
Oh, really?
Yes. At least it used to be. So, like with Canoe and Falcon, currently you can assemble Drosophila maybe within 1,000 CPU hours. So it's like magnitudes faster now, but it is still not as fast as Flye. So Flye can assemble a Drosophila in I think we have this number in the paper, and so like wall clock time, it takes maybe it runs overnight. So this must be maybe 100 or like a few hundred CPU hours. So it's typically 5 to 10 times faster than Canoe.
That's very impressive. So let's talk about the secret sauce that Flye uses. So the core idea, as I understand it, or the core insight to spitting it up, is realizing that you don't need to error correct the reads, but obviously you do, right? There is a good reason why people used to error correct. So what do you replace that with? How do you have a good assembly without error correction? What was the insight that allowed you to skip error correction?
So this was originally developed in the Bruijn assembler. And the insight was that it was basically the Bruijn graph. And this was originally proposed by Pavel Pevzner, I believe, in like early 2000s.
So what is an Bruijn graph?
So Bruijn graph is, you can think about it as a generalization of the Bruijn graph. So in the Bruijn graph, you can think about a construction process of the graph. So what you do, you take your reads, you split them into sequences of k-mers, and then you glue the k-mers if they spell the same sequence. So a Bruijn graph says, okay, we have an abstract set of reads and like abstract sequences, and then you can glue them based on whatever criteria you want. And you can use local alignments to glue sequence instead of k-mers. And this way you can actually tolerate some noise in your reads. But yes, you can think about Bruijn as a generalization of this graph construction phase of the Bruijn graphs.
Mm-hmm. So do you glue k-mers still, or do you glue the whole reads?
You can define it in a different way. So this is a sort of a framework, and it depends on the application. So, for instance, in Flye, we glue sequence based on local alignments. But originally in Bruijn, we proposed to glue k-mers, but instead of gluing all k-mers, as in the Bruijn graph, we were gluing some k-mers. And so this sort of like, we slightly changed the rules of gluing, and this is why we call it a Bruijn graph, because it's sort of generalized version.
So when you say in Flye you glue sequences, it means you do pairwise local alignments of all the reads against all the other reads, and you glue only the parts of the reads that locally align to each other.
Yes.
Mm-hmm.
But this sort of started from we using the ideas that were described in a Bruijn paper, and basically the idea was that, okay, so we have noisy reads, and most of the k-mers in these reads are erroneous. Even short k-mers, even k-mers of size 15, and for comparison, the short read assemblers, for luminary read assemblers, they use maybe 50, k equals 50. In short reads, we use k equals 15, and still, if you enumerate all the k-mers in your reads, most of them will be erroneous because they will likely contain errors. But there are some correct k-mers.
So aligning all the reads against all other reads sounds very expensive, right? The alignment algorithm itself is, let's say, quadratic, and then you have a quadratic on top of it, which is all against all. How do you manage to make that fast?
So in Flye, we introduced something we called disjointics. And yes, you're right. It is expensive to align all reads against themselves, and this would be like a step back to this error correction techniques. In Flye, we introduced disjointics, and disjointics they're sort of similar to contigs, and the idea is that you can build these disjointics really, really fast, and you will cover your entire genome with these disjointics, and then you can build your graph, and then you can compute alignments, pairwise alignments of these disjointics and build the graph. But instead of working with the whole set of reads, you will be only working with these disjointics, so your like search space will be reduced significantly.
So do you want to explain what a contig is for those who don't know?
Right. So basically the contig is a part of an assembled part of the genome. So contigs are typically the output of genome assembler. And this is because usually genome assemblers cannot recover the entire whole original genome sequence. And this is because there are some ambiguities in the graph caused by repetitive regions in the genome that could not be sort of resolved. You cannot distinguish between long copies of repeats within the genome. And this is why you cannot reconstruct the whole genome sequence, but you can reconstruct parts of it. And these parts is what we call these contigs. So a set of contigs covers your entire genome, but the order of these contigs is unknown. So you get like a set of sequences, and you know that they represent your genome, but you don't know the structure of the genome. And this is actually where long reads come into play, because with longer reads, you can resolve more repeats, and thus your assembly will contain less contigs, so it will be less fragmented.
Right. So the fewer contigs we get and the longer contigs we get, the better the assembly is.
That's true. So, and the idea of Flye is, given the set of reads, we can generate this set of, sort of draft contigs. We call them disjointigs because they are sort of less accurate than, these contigs that you'll get in the end of the assembly process. So we sort of construct these draft, disjointigs, using a greedy approach. So we simply take, a random reads and try to extend it left and right based on this, based on the overlaps. So we take a read and we find all overlapping reads, from your set of reads. And then you, select any of those reads and you extend, and then you continue this process. So it's kind of like a greedy extension. And we can do this really fast because we do not compute all pairwise alignments. We only compute alignments for reads that sort of became parts of disjointigs. So this is why we can do this really fast. But on the other hand, we do not guarantee that the disjointigs are very accurate. They might contain incorrectly resolved repeats because we do not attempt to resolve them at this stage. But the idea is that we can generate this set of disjointigs really fast, and then we can build a Bruijn or repeat graph. So in Flye implementation, we call the graph that we are constructing a repeat graph. But you might think of it as a sort of a implementation of a Bruijn graph framework. And we can construct this repeat graph from disjointigs, and it sort of fixes the issues that disjointigs possibly have had. And in the end, we can sort of result into this repeat graph really, really fast. We can generate it fast. And it's free of errors in the end once it's constructed. So this is the idea how we basically speed up the graph construction process.
Right. So your repeat graph is sort of like an Bruijn graph, and an Bruijn graph is in turn sort of like the Bruijn graph. So like for people who are familiar with the basics of genome assembly, but are not keeping up with all the publications. So you can imagine it as a sort of de Bruijn graph, right? And so your disjointigs, they spell out some paths,
right,
on the de Bruijn graph, not necessarily the same paths that the genome itself spells.
Yes, basically yes. So you may think about disjointigs as a random walks on the genome graph. And this could be like, it could be a repeat graph, or you may think about this as a de Bruijn graph. And disjointigs essentially represent walks on these graphs. And they do not necessarily correspond to the genomic path, the correct genomic path, because as I said, they might have contain incorrectly resolved repeats. But once the graph is constructed, we basically have all these incorrectly resolved repeats collapsed. And this is the intuition why this sort of fixes the errors. And after the graph is built, we apply the conventional procedures that were originally developed for deep Bruijn graphs for short tree sequencing, such as repeat resolution. So I think as I was telling you in the beginning, we align reads on the repeat graph, and when we resolve repeats, this time we resolve them accurately, and then we generate your final context sequence.
Right. So you keep bringing up the repeats. So let's talk about repeats. Why do they cause a problem for assembly, and what does it mean to resolve a repeat?
So the problem with repeats is, let's imagine you had a genome with no repeats at all. So the sequence is purely unique. In this case, you should be able to assemble the genome, the entire chromosome, really, really easy.
Because there's just one way to stitch together all the reads.
Just one way to stitch together all the reads. Once you have repeats, it's more difficult because once you hit the repeat, you don't know which copy of this repeat is it. And it could be like in multiple places in the genome. And you need to be really careful, because you may sort of jump from one location of the repeat to another location of repeat, and this will result in something that we call a misassembly, when you like artificially join two different regions of the genome. So, and to distinguish between repeat copies, you can imagine that you need a read that is longer than the repeat. So this way the repeat kind of bridges, the read bridges the repeat, because it has unique anchors on the left and on the right side of the repeat that we can use to tell, okay, this repeat came to like this position, from this position of the genome, because we know this unique sequence is adjacent to this unique sequence on the left and on the right. Basically to resolve this repeat, and this is the idea behind the resolving repeat, you need reads that are longer than repeats, and you need unique sequence anchors. And the problem is basically you need to identify repeats in your reads, and you need to encode them somehow to resolve them accurately. And this is actually why the assemblers use different kinds of graphs. So we think it is critical to encode these repeats and to know where they are in the graph in the assembly to accurately resolve them. And the Bruijn graphs, one of the benefits of deep Bruijn graphs and related graphs such as repeat graphs that we use is that they explicitly encode repeats, and they give you the boundaries of these repeats. They tell you where these repeats are.
How exactly do they encode repeats?
Well, basically, you will have edges that correspond to repeat sequence. So some of the edges of your graph will correspond to the unique sequence, but other edges will sort of encode the repeats, and the junctions between these edges will correspond to the boundaries of repeats. And a simplest example of a repeat could be that you have one single edge that is a repetitive edge, and you have two unique sequences that enter this repeat from the left side. And then you have two unique sequences that exit this repeat on the right side. And sort of if your unique entrances are A and B, and then the exits are C and D, this repeat sort of allows you two transitions. It allows you to transition from A to C and from B to D, or it allows you to transition from A to D and from B to C. And this sort of creates the ambiguity, because you don't know which path corresponds to the correct genome path in the graph. And we are looking for this kind of structures when we when we try to classify each edge as either unique or repetitive.
So to go back to Flye, so the pipeline of Flye looks like this. So first you compute the disjointics, and I think we talked about how you do that. So you keep extending the reads.
It is very simple. We just keep extending reads until we're done, basically, until we hit some sequence that is already assembled.
Right. And only at that point you actually start building a graph, right?
Yes. We start building the graph after we basically based on the disjointics that we have constructed.
Right. So how does that process work?
So we take our disjointics and we do pairwise alignments between, we compute all possible local alignments, within this set of disjointics. But it is easier to do than computing pairwise alignment between, the entire set of reads because you have much less sequence now. So, disjointics sort of compactly represent your read sets as it's kind of like, simplifies the read representation. So you like condense, you collapse all your redundancy in reads into like a single disjointic or multiple disjointics.
So it's sort of like a consensus sequence.
Yes, exactly.
Mm-hmm.
And we compute the local alignments, and then the idea is that we sort of glue the sequence that was aligned, and this sequence, this glued parts will be, most of them will be the repetitive parts. So we take these local alignments and we glue the sequence, and we result into a repeat graph. So compare it with a Debian graph construction. In Debian graph construction, we glue all k-mers that spell the same strings. In repeat graph, we glue the sequence that was aligned that is highly similar. So this is essentially the same idea, but with a different implementation because it is difficult to apply Debian graphs to long reads directly because of the high error rate, and we compute the local alignments allow us to tolerate this high noise of long reads. So that's the idea behind repeat graphs. We want to use this similar framework to Debian graphs because there's a lot of methods that have been developed already, and we want to reuse them. But to construct the graph, we need to be more creative because of the high noise rate.
Right, that makes sense. So once you have a repeat graph, you can apply all the algorithms for the Bruijn graphs. But can you walk us through those subsequent steps?
So, well, the most important part is repeat resolution. So once you have your graph constructed, you have all repeats of that are longer than some predefined threshold revealed on the graph as edges. And we typically use threshold. We typically collapse repeats of size longer than 1000. And for most of the datasets, this threshold is even higher. So it could be 3000 or 5000.
So can you explain what that means? What does it mean to collapse or not to collapse a repeat?
So, like in terms of construction, let's say we have a threshold of length 3k. This means that we will only store local alignments that are longer than 3k. And all the repeats that are revealed on the graph will also be longer than 3k. And we sort of ignore the repeats that are shorter, which greatly simplifies the structure of the graph. And this is how Debian graphs and short-read assembly approaches are different. So in short-read assembly approaches, on Debian graph, you will get repeats that are very, very short. That could be, say, like all repeats longer than 50 base pairs will be on the graph. And this complicates the graph structure a lot because you have more in genomes, this is sort of an exponential distribution of read length. So you have a lot of shorter repeats, and once you increase your threshold, you'll get less and less repeats. And like on bacterial genomes, there are only a few repeats. Let's say on the E. coli genome. So bacteria at different bacterial genomes are very different, but let's say for E. coli genome, there are only maybe 7 repeats that are longer than 5,000 base pairs, and no repeats that are longer than 7,000. And because we have long reads, we can basically increase this repeat length threshold, because we kind of bypass the shorter repeats. They're like sort of stay inside the reads, and we do not care about them, because we like sort of we compute the alignments that are longer than repeat length, so we're kind of safe.
Nice. And right, so you were telling how the repeat resolution works, I think.
Yes. So repeat resolution, basically we have our graph with repeats collapsed. By collapsing, I mean that original repeats in the genome, they are collapsed into a single edge on the graph. And then we take our original reads and align these reads to the graph. And now let's think about this simple repeat example that I was telling you about. So there are 2 entrances A and B and 2 exits of C and D. And if you see that all reads consistently take one of the paths but not the others, so let's say most of the reads align to traverse A, then they enter the repeat and then they exit at C, and like the second half of the reads enter B and then traverse the repeat and exits and at D, then we know actually this tells us how the genome traverses this graph. And if we consistently see this support by reads, we can simplify the graph by sort of separating these 2 repeat copies into 2 separate paths. And this is what we call repeat resolution. So if we see an evidence from reads that genome takes one path but not the other, we can separate this part of the genome path. And this way we simplify the graph.
Okay, so now you have a simplified repeat graph, which has, I guess, more edges but fewer junctions.
Yes, exactly.
And what do you do next?
And so next is basically, as we said, it has slightly more edges, but yes, it's less tangled. It has less repeat junctions because some repeats are resolved. And as a result, you will have like a long non-branching paths on this graph as a result of repeat resolution. And these non-branching paths will correspond to the reconstructed genome sequence, and this will be your contigs, basically. So after repeats are resolved, we generate contigs as non-branching paths on the final simplified graph. And this will be the output of the assembly of the genome assembler.
So some of those contigs will be simple contigs, but some will be unresolved repeats, right?
That's right. So yes, in reality, it's a little more complex because, let's say, let's think about this repeat example again. So let's assume that this time you could not resolve a repeat. You could not, because it was longer than the contig length. Oh, okay. Because the repeat length was longer than the read length. You were not able to resolve this repeat. But then you have your A and B entrances, and you know that that repeats always. So you know that the genome path goes from A inside the repeat. but you don't know how it exits. But, you still know that the repeat, like the unique part A ends with a repeat. So when you're generating contigs, you basically can extend the unique edge A with the repetitive sequence. So it increases the length of your contigs a little bit, and it also simplifies the representation. So most of the contigs will be representing the unique parts of the genome. And we also try not to sort of so in this example, we will extend contigs A and B to the right inside the repeat, but we will not do this we will not extend the exits C and D to the left inside the repeat, because it will kind of like create artificially duplicated sequence. So we want to avoid that. But yeah, so this is the idea of contig generation. We take the non-branching paths, we take the unique non-branching paths, and try to extend it into the repetitive parts in the graph if there's no ambiguity in terms of how the genomic path goes, until we sort of hit the ambiguous junction. Then we stop.
So this process gives you a set of contigs, which are separate sequences, right? But when we download a genome build, let's say of Drosophila or of human, in the FASTA format, then we have a single sequence per chromosome, right? It's not a set of contigs per chromosome, which is a single sequence. So how do you put those contigs together in a single sequence?
Okay. So this is, yes, so you're right that for, let's say with long reads for bacterial genomes, you will most likely get your entire chromosomes assembled, and maybe for simple eukaryotic genomes as well. But you're right that for more complex genomes such as Drosophila or human, we will not get the whole chromosomes. You'll get a few contigs per chromosome. And then you need to somehow assign your contigs to chromosome and assemble. And this is what people call genome finishing. This is a whole different process, and there are many different techniques. So, and they also evolving and changing constantly. So in this, there are a few things you can do. You can try to use complementary technologies to basically what we call scaffold your contigs into more contiguous sequences. Let's say, and there might be different ways to get this evidence of the order. So you basically want to order your contigs. And for instance, there is, one simple way could be if you have some sort of genome map. It could be a genetic map, or like restriction map. So you sort of have an idea how the chromosome structure looks like, and you know the approximate location of the genes on your chromosome from some genetic studies. And then you can locate these genes on your contigs. And if you have two contigs and you know that's like two genes on these contigs follow each other, they are close on the chromosome, you can sort of stitch these two contigs together. So, and there are many biotechnologies that allows you to do this, not based on genes, but based on different information, such as Bionano. Bionano is basically a technology that allows you to get a chromosome maps based on, I think, restriction. This is sort of restriction maps. So, you can put a long chromosome fragment in a machine, and it will, cut it at a particular locations which are recognized by some enzymes. So if you have like a particular nucleotide pattern at some location, enzyme will cut it. And then you can visualize this restriction map. And you can basically do this computational for your reconstructed contigs as well. And then you can compare these two restriction maps, and this will might tell you how to order your contigs so they sort of consistent with the restriction maps that you're getting. And there are other technologies such as Hi-C. So with Hi-C, you get pairs of reads that come from related regions of chromosomes. And if you have these pairs of reads that consistently allows a line to like a pair of contigs, then you can say that, okay, these contigs, they must be connected together in the genome. And you can use the complementary sequencing technologies as well. But usually genome finishing is like a very long and time consuming process. And at this stage, you also need to make sure that you need to do a lot of quality controls. So, but I think with long reads, this process becomes simpler because you have longer assemblies in the beginning, and also there are more biotechnologies that like can help. So this field is improving rapidly, like genome finishing, and in the past few years we started to get like more and more complete or almost complete genomes. But there are still challenges, yes. If you think about this, human reference genome is technically not complete yet.
Mm-hmm.
Yes, you get entire chromosomes, but there are gaps in the chromosomes. So there are like parts filled with ends. If you look in the FASTA sequence, you see like a long stretch of ends, like megabytes of ends. And this means that we don't know the sequence inside this region. We know the order. We know that there's something in there, and we know the order of the adjacent sequence, but we don't know what's inside. And this is why we actually need long reads. I believe we can use long reads to fill these gaps. And there are actually ongoing efforts to finally finish the human genome using the ultra long Oxford nanopore reads that basically allow you to span these gaps in full or almost like entirely.
Yeah, didn't they finish the human X chromosome recently?
Yes, they recently announced that they assembled the X chromosome in full, and the most difficult part was to assemble the centromere region, because I believe it's roughly 3 megabytes long, and it is not yet possible to produce reads that like are this long. So you might get reads maybe over 100,000 and maybe a couple of hundred routinely. And then you need some creativity to basically stitch these reads together and span this centromere. And the challenge is that centromere is basically a tandem repeat that is repeated many, many times. So you may think about this like a 200 base pair sequence that is repeated millions, all hundreds of thousands times in the centromere. So, and you still somehow need to assemble through it. So this is like, I think, a very interesting challenge that people will focus in the future.
Definitely. So one way to judge the quality of an assembly is the classic metric, which is called NG50, but you also propose a modified version of that metric called NGA50. So can you talk about these two metrics and what is the difference between them?
Okay, so, well, NGA50, I think, was originally introduced in, I believe in one of the, Assembleton studies, or maybe Gauge. So they were like, early studies that were evaluating the quality of many different short read assemblers. So, and they were like introducing different metrics. And then it was implemented in the Quast, quality assessment tool for genome assemblies. And now it is one of the, default and I believe one of the most important metrics, for quality assessment. So basically, let's start from N50. So original N50 was the quality metric for genome assembly. And as we were talking about, the longer your contigs are, the less fragmented they are, the better assembly is. But the number of contigs sometimes might be misleading if you simply count the number of contigs, because you might have, it doesn't take into account the length distribution. So you might have a few really, really long contigs, but maybe thousands of short contigs that could be artifacts of the assembly process. And this will inflate your contig counts. So N50 was introduced such as a sort of like a weighted measure that takes into account the length distribution. And it is defined as, so N50 is so let's say you have all your contigs sorted from the longest to the shortest, and you start, taking, and you're going from the left to the right, and you're taking your, the longest contigs until your set of contigs cover the half of the entire assembly size. And the length of these contigs that you took last will be your N50. So essentially, the contigs that are longer than N50 covered half of your total assembly size. And this is a very, like, this is one, I believe, the most popular metric for genome assembly comparison. And NG50 is very similar, but instead of covering the assembly size, you need to cover the genome size. And this is because the assembly size might be shorter than your target genome size. Because of the collapse repeats, because of some missing sequence, there could be different reasons. And NG50 also allows you to compare multiple assemblies, because multiple assemblies might have different size as well. And NG50 sort of like is a common denominator for multiple assemblies comparison. Okay, so now NGA50. So there's like a letter A, extra letter A, and it stands for alignment. So the problem with NG50 is that it doesn't evaluate the correctness of the assembly. And you might think about this as let's say you have your assembly. How can you improve it? How can you improve N50? Well, you can just simply concatenate all your contigs together, and you get like a perfect N50 or an NG50, but will it be a correct assembly? No. So what NGA50 does, or NA50, is you align your contigs if you have a reference genome. So this is a reference-based metric. And a reference genome is basically your gold standard for your assembly. And this is something that you can compare to, and you can evaluate your algorithms. And typically, you don't have reference genomes for like completely novel organisms, but you have reference genomes for organisms that already have been sequenced, or you might have. So, okay, NGA50 is a reference-based metric. And what you do, you align your contigs to the reference genome. And then if you see any breakpoints, if you see that a contig is, kind of like one part of the contig aligns to one region of the genome, and the other part aligns somewhere like to a completely different part of the genome, then you can split this, contig into two parts. And NGA50 is basically NG50 computed on this, contigs that are broken at these inconsistent positions.
So you try to undo the cheating.
Exactly.
Okay, and so you compared your tool with the other assemblers, and in terms of NG50 and NGA50, and what did you find?
So we found that that Flye typically on many genomes it consistently performs equally well, and sometimes better on some on various genomes that we were benchmarking, such as East genomes or C. elegans genome, and we significantly improved on Canoe and Mazurka assemblers on the human genome assembly, and this is measured with this NGA and NG50 metrics, as well as the number of. We also evaluate the number of errors based on the structure comparison that I described. And on the human genome, we were also significantly faster. We were, I believe, roughly 10-fold faster than Canoe and Mazurka. And Mazurka is a hybrid assembler, actually. And we see the similar trend for other genomes that we compare as well. So we typically as good as the other assemblers, and sometimes we improve. And we're also consistently faster. And right now we also work on sort of expanding Flye to metagenome assembly, and this presents additional challenges, such as when you're assembling a multiple, so you're essentially assembling multiple genomes simultaneously instead of just one genome. So you can imagine that the problem is much more difficult.
Very cool. Mikhail, it was a pleasure to talk to you, and I really like your work. There are both nice theoretical ideas around this disjointics and how to build the assembly graph, and also very impressive practical results in terms of the runtime of the program and its performance. So pretty cool tool, and
thank you.
I'll look for an opportunity to try it out.
Yeah, for sure. Thank you, Roman. Thanks for having me. It was really interesting to talk to you and sharing our most recent results. And I think it's a great way to communicate to other people who are interested in bioinformatics. So yeah, thanks a lot for inviting me.